Have you ever stopped to wonder how you can watch a perfectly crisp 4K movie on Netflix or YouTube without it just buffering forever? Well, the answer comes down to a piece of tech you use literally every single day, but probably have never even heard of. It's a video compression standard called H.264. And really, it's the invisible engine that made our modern streaming world possible. So, how on earth did this revolution happen? Let's dive in. To really get our heads around the magic of H.264, we're going to start with the massive problem it was built to solve, the Gigabyte problem. Then, we'll peek inside the engineer's toolkit to see the 4 core ideas behind all compression. From there, we'll see how those tools were cleverly adapted to handle motion. And finally, we'll see how H.264 put all these pieces together to completely change video forever. All right, so first things first, we need to appreciate the sheer scale of the challenge here. The biggest problem with video, right out of the gate, is that it's just an astronomical amount of data. To put this in perspective, just one single minute of raw, uncompressed HD video is over 12 gigabytes. I mean, that's bigger than a lot of modern video games. Trying to stream or download that over an internet connection from the early 2000s, it wasn't just slow, it was fundamentally impossible. Something had to change, and it had to be drastic. And that leads us to the core challenge of all compression. It's this constant tug of war between two things: the bit rate, which is just a fancy term for file size, and distortion, which is the loss in quality you can see. The goal is always to get the smallest possible file with the least noticeable drop in quality. This balancing act has a name: rate distortion performance, and getting this right is the holy grail of compression. So how do you actually shrink all that data? Well, for decades now, engineers have been using this powerful 4-step playbook. It's kind of the universal pipeline for all digital compression. Okay, let's slow down here for a second, because this is the foundation for everything. Step 1 is prediction. Imagine a blue sky in one frame of video. You can pretty safely guess it's still going to be a blue sky in the next frame, right? So you only need to record the changes, the residual, like a bird flying by. Next up is transformation. This is kind of like taking a musical chord and breaking it down into individual notes. It converts that change data into different frequencies, which lets us separate the crucial details from the less important background noise. Then comes quantization. Now, this is the really clever but also sacrificial part. This is where we strategically throw away a little bit of information to save a ton of space. It's like saying about $10 instead of $9.97. You lose a tiny bit of precision, but the data gets way simpler. And finally, entropy coding. This is like a digital shorthand. It uses short codes for things that appear all the time and longer codes for things that are rare. It's the final step to pack everything down as tightly as possible. Now, those 4 tools work great for a single image, like a JPEG you'd take on your phone. But video isn't just a slideshow of separate pictures. The real magic comes from exploiting the relationship between the frames over time. And this is the key difference. On one hand, you have intracoding. Think of this like taking a brand new photograph for every single frame and compressing each one individually. But on the other hand, you have intercoding. And this is where the genius comes in. It looks at a new frame and asks, hey, what's changed since the last frame? By only encoding the differences, you save a massive amount of data. This is really the big idea that separates video compression from simple image compression. So just looking at what's similar between frames, that's a huge step forward. But the biggest reason frames change in a video? Well, stuff moves around, right? So the next great leap was actually teaching the code how to understand and describe that motion. But wait, there's a problem. If you have a ball moving across the screen and you just subtract one frame from the next, the computer sees 2 big changes: a hole where the ball used to be and a new ball in its new spot. That simple difference method is actually super inefficient. So how do you get around that? The solution is absolutely ingenious. It's called Compensated Prediction. Instead of sending all the new pixel data for where the ball moved to, the encoder just finds the ball in the previous frame and sends a tiny instruction, a motion vector, that basically says, hey, take that block of pixels and just move it 5 spots to the right. It's so much more efficient because you're describing what happened instead of sending a whole new picture. And this core idea just got better and better over time. Engineers made motion prediction way smarter in a few key ways. First, they increased the accuracy of those motion vectors down to 1/4 of a single pixel. That's incredibly precise. Then they introduced variable block sizes, which is super smart. You use big blocks for simple areas, like a wall, and tiny little blocks for complex things, like a person's face. And they even let the system look back at multiple previous frames, not just the last one, to find the absolute best possible match for any moving object. And this is where H.264 enters the story. It wasn't one single revolutionary new idea. Instead, it was the masterful culmination of decades of these small, brilliant improvements, all perfectly optimized and combined into one incredibly efficient package. Don't just take my word for it. The actual creators of the standard said it best themselves. H.264's real power doesn't come from one big thing, but from a plurality of smaller improvements that all add up to a massive leap forward. So what were some of these crucial improvements? Well, this table lays out a few. Instead of the older, larger 8x8 transform blocks, H.264 used smaller, more precise 4x4 blocks that were way better at handling fine details. As we just saw, it swapped out rigid fixed motion blocks for flexible, variable-sized ones. And here's a huge one. It added a smart deblocking filter inside the main processing loop to clean up ugly compression artifacts on the fly. And finally, it used way more advanced entropy coding that could actually adapt to the context of the video, packing the data much, much more tightly. And what did all that technical stuff actually mean for the video you were watching? The results were massive. The smaller transform size meant you got cleaner video with less of that blurry noise around sharp edges. That deblocking filter was a total game changer for visual quality. It got rid of the ugly blockiness that plagued early digital video. And that smarter entropy coding? By itself, it squeezed out another 10 to 15% in file size savings. Every single piece made a difference. So we've gone through a lot of the tech, but let's bring this all home. Why should you actually care about any of this? What was the ultimate impact of all these clever engineering choices? This chart tells the whole story. It's measuring visual quality. Basically, the higher the bar, the better and cleaner the video looks. And you can see that for the exact same amount of data, the same bit rate, older standards like MPEG-2 gave you, okay quality. But give H.264 that same amount of internet juice, and it just blows the others out of the water, producing dramatically higher quality video. So how much better was it? This right here, this is the magic number. H.264 delivered about a 50% savings in file size compared to what came before it. It literally cut the amount of data needed for a good-looking video in half. This wasn't just a small step up, it was a revolutionary leap forward. And that right there is why everything changed. Cutting the data requirement in half is what finally made it possible to send high-definition video over the average internet connections people had in the mid-2000s. Without this 50% gain, there's no YouTube HD, there's no Netflix streaming. The internet, as we know it, simply wouldn't have been viable. This unlocked everything. So H.264 wasn't just an update. It was the engine that built the visual internet. And yeah, newer, even more efficient standards have come along since, but this was the big one, the revolutionary leap that made it all possible. And it leaves you with a final thought. If a 50% gain in efficiency unlocked HD streaming for the entire planet, what in the world will the next great compression breakthrough make possible?